So these are all the important problems that can be solved under this iterative improvement algorithm design technique. One is the simplex method. Second one is the uh, maximum flow problem or Ford-Fulkerson algorithm. The third one is maximum matching in a bipartite graph. The fourth one is stable marriage problem or Gall-Shapley algorithm, local search heuristics. In this video, we are going to discuss about how to find the maximum flow in a network. Maximum flow problem. So what is a maximum flow problem? So a problem of maximizing the flow of a material through a transportation network. Example, the pipeline system or communication or transportation network. Okay. So if you have to carry a one data from source node to destination node, say in the case of a network system or in a communication system. So we may not aware of that when you are forwarding a packet or a data from source to destination, it may go on a different way or the path where it is available, isn't it? So each and every node will have some capacity. Okay, in the source node you are sending some size of packet. Okay, so it may be passed on to the some intermediate node before reaching into the destination. No, and also you should know that what may be the capacity of the node. So each and every node may pass the data according to its capacity. So from node 2 to node 3 you can able to transfer only 2 Mbps. Okay, so you cannot pass the data or forward the packet which have more than that size. Okay, so accordingly it may be divided and it will reach into that destination. So that is an example of the maximum flow problem. So you have to transfer some material that can be of anything. Okay, for example, if you consider the water pipeline also, if the capacity is having the flow into that pipe is only this some 1 liter. Okay, so you cannot force more than that capacity into that pipeline. Okay, so our aim is you have to transfer the material or pass the material from the source to destination. Okay, in such a way that you have to maximize the flow. So how can you model this problem? In the sense, you can represent this Maxflow problem as a connected weighted graph with n vertices. Okay, with the following properties. Okay, so it has to contain exactly one vertex with no entering edges, that we call it as an source. Okay, and it contains only one vertex with no leaving edges called the sink. So that's what you have to send the material from source to destination. Then each and every edge will have some positive integer weight that we call it as an uij. That's what I have said. Each and every node will have some capacity. Okay, so uij is nothing but then the capacity on that edge. So that is only that much flow can send from the node I to node j. Okay, that we call it as an edge capacity, indicating the upper bound on the amount of material that can be sent from the node I to node j. So you can model this problem as an one connected weighted graph. So this is an example of a flow network. So here you have some 6 nodes. Okay, so you know that the source is a vertex which doesn't have any incoming edges. So we marked the node 1 as a source. Okay, then whereas 6 is the sink, the node which doesn't have any outgoing edges. There is no leaving edges from this node. So we mark this 6 as a sink. Okay, so the max flow problem is you have to maximize the flow from the source to destination. Then you have to find out the path where you can maximize the flow. Okay, or how much flow can be transferred from source to destination. Okay, where this edge weight between 1 and 2 represent as a 2, which is nothing but the edge capacity. So this much flow only can be transferred from node 1 to node 2. That is the meaning of this edge weight that we call it as an edge capacity. Definition of a flow. Yeah, flow is an assignment of real numbers xi j to edges ij of a given network that satisfy the following. So that is, you are assigning some real numbers on that edge I comma j, that we call it as an xij. Okay, it's going to be one real number. Okay, there is some constraints on that flow. It has to satisfy flow conservation requirements. What is the flow conservation requirements? Is the total amount of material entering an intermediate vertex must be equal to the total amount of the material leaving the vertex also. Okay, suppose if the 2 is entering into that thing, so the same has to be out. Okay, so that intermediate vertex cannot have an rights to add the flow or decrease the flow. Okay, so xji is equal to sum of xij for I is equal to 1 to n minus 1. Then next, capacity constraints. Okay, so obviously that is the flow should be less than or equal to capacity of the edge, and automatically it should be greater than or equal to 0. Okay, that is the capacity constraint. So this is your current flow. This is the capacity of the edge. So always the capacity should be greater than 0 and it should be less than or equal to this capacity. Next, what is flow value and maximum flow problem? So what I said, since no material can be lost or added to by going through the intermediate vertices, the total amount of the material leaving the source must be end up at the sink. Okay. So that is summation of x1j, this is a source, okay, equal to xjn, that may be the sink. So it may pass on to the sum of the intermediate vertices also. So the value of the flow is defined as the total outflow from the source. Okay, that is the total inflow to the sink. So what is the maximum flow problem is to find a flow of the largest value for a given network.